And we are live. Hello, everyone. Welcome to today's Neurotheory Forum, part of Worldwideneuro. I'm Everton Agnes, project leader at the Biozentrum, University of Basel in Switzerland. And today I have the pleasure to host Professor Tatiana Sharpie. Tatiana is a professor at the Salk Institute for Biological Studies, where she's the Helen McLaughlin Developmental Chair in Neurobiology. Professor Sharpie obtained her bachelor's degree in physics from the Taras Shevchenko National University of Kiev, Ukraine, and then moved to the United States for her PhD. In 2001, Tatiana obtained her PhD degree from Michigan State University under the supervision of Mark Dickman and Phil Platzman. After her PhD, Tatiana decided to switch from physics to neuroscience. She then became a Sloan Swartz postdoctoral fellow at the University of California, receiving in 2015 a National Science Foundation grant to study feature selectivity and invariance in the cortex. And in 2018, Professor Sharpie was elected Fellow of American Physical Society. Tatiana is interested in sensory processing and how information is represented in the brain. And over the years, she has studied the visual, auditory, and more recently, olfactory systems. Professor Sharpie uses methods from physics, mathematics, and information theory to help us understand how the brain works. I'm very interested in Tatiana's work on how to make sense of neuronal activity and the underlying dynamics of these activity patterns, especially in information content in the activity pattern of neuronal populations, a topic that Tatiana will cover today in her talk. So before we start, just a few reminders. We have a chat on the right, so use the chat as much as you want. If you have questions that you like to be answered during the talk, write them there and I will ask Tatiana. Additionally, there is an Ask a Question box at the bottom of the page, so use it to post questions that you like addressed at the end of the talk, and then I can invite you on screen to ask them. And we will have a Zoom meeting with Tatiana after the talk for further discussions. I'll paste the link on the chat. And with no further ado, Tatiana, the online stage is yours.
Thank you very much for the kind introduction and for the invitation to discuss our work here. Today I will be presenting joint work with recent graduate John Berkowitz, who received his PhD from the University of California, San Diego. And the results I will be describing to you are about how to transform neural responses or arrange neural responses such that they can be read out without information loss in principle. So as a brief motivation, I would like to start with a concept in psychology called schema plus correction. So it means that if I show you this crumpled Coke bottle, and then to explain what this is, one easy way is to say, well, here is a noiseless system, and then it has been crumbled. So schema plus correction. So that's the theorist approach to the understanding neural circuitry. We have a complicated circuit with wires that we don't, maybe it's difficult to discern how the goal of the transformation. So we start by understanding what are the ideal ways that the system may want to approximate. So today, the main part of my talk will be this part number 1, about how neural responses can be structured such that they can be transformed in subsequent transformations without loss. The information in the context of this talk will be mutual Shannon information. And then a second, shorter, more technical part, potentially just a few slides, will be quantifying information conveyed by large neural populations. So we will take the algorithm and the equation that I will derive in part 1, and then discuss how it can be numerically evaluated and what are the limitations and technical limitations of the approach. So to start, I would like to start with classic results by Georgopoulos and colleagues. and with a notion of population vectors. This is a widely used measure of readout for neural activity. And originally it was demonstrated in the motor system. So here is an example of motor recordings from a motor neuron. And the animal is making different directions of movements. And one can see in this figure that each dot here is a response of the neuron, a spike, across multiple trials, maybe 10 trials here. And we can see that when the animal makes the movement down to the right in this direction, then neuron produces many more stronger responses than in the opposite direction. So using this observation, Georgopoulos proposed that if each neuron has its preferred direction of movement, then, and these preferred directions of movement differ across neurons, then if one averages these preferred directions, so in this case, down to the right for this neuron, by the amount of spikes that each neuron produced, then it turns out that the resulting vector, so population vector, will provides an accurate representation for the direction of movement in that the animal actually makes. So that's a way to connect neural activity with behavior. Or for example, this method has also been used in visual neurons, in which case the W will represent the most relevant visual pattern for a neuron. And then when averaged with the neural responses, it will produce an estimate of what the stimulus was that evoked the population activity that we are measuring. And this is a very popular measure. However, it makes several strong predictions that can be tested. And these predictions were not quite borne out. So one of the key predictions in this population vector is that if you have neurons that have the same preferred directions, then one can just average their responses and nothing else matters. So one can check this. So the identity of the neuron beyond its preferred direction is not relevant according to this equation. And so that's the key assumption that several groups have tested. And one of the examples is, for example, this work from Jonathan's Victor laboratory, where on the x-axis we have number of neurons. So these are maybe early days, but simultaneously recorded neurons. And they're comparing two versions of the ways of decoding neural responses. One version is a population count, meaning these are neurons that are nearby, presumably with similar preferred stimulus patterns. And one can compare information in bits per second conveyed by this neural population with computed in two ways, as a labeled line code or a population count. So in the population count, we average neural responses, and in the labeled line, we keep track of which neuron produced the response. So in this simple hypothetical table, we get that suppose we have stimulus 1, 2, and 3, and stimulus 1 evokes responses from neuron 1, stimulus 2 from neuron 2, stimulus 3 from neuron 3, but and not in other situations, then the count will have convey no information about the stimulus, but one can perfectly recognize the stimulus if we keep track of which neuron produced the spike. So that's the argument for why, in general, the labeled line code would be useful in the brain. And indeed, in this work, they showed that it does convey more information. So if we reduce our readout mechanism to just averaging neural responses, we will lose information. So in this case, maybe the receptive fields, as they're known, or preferred stimuli for these neurons were maybe not quite identical. So one can analyze another case. So this is the work by Leslie Osborne together with Stephanie Palmer, Steve Lisberg, and Bill Bialek. The responses of hypothetical neural population that is constructed from real neural responses. So in this case, how would this population respond for a stimuli that were shifted or measured relative to a preferred direction for a neuron? So by this construction, all the neurons automatically have the same preferred stimulus direction. So in this case, this is also in the motor system, and this is with respect to the eye movements. And these are actual tuning curves of neurons that were, so what is shown here is the normalized rate of the neuron as a function of the target motion on the screen relative to preferred orientation for that neuron. So these neurons were recorded separately, but one can put this together, ignoring noise correlations, to a first approximation. And what they are showing is that if the stimulus is a certain degree from the preferred stimulus direction, then one can observe how each of these neurons would be responding and form the so-called words, or effectively to the labeled line code. And in this case, the analysis extends to more neurons, and one can clearly see that keeping the identity of neurons here conveys much more, again, Shannon mutual information compared to what is available if we just average the neural responses. So that was a direct test of the population vector equation, and it shows that the width of the tuning curve around the preferred direction also matters, and maybe there are other parameters that of neural responses that matter. And the question is that this code, where we keep track of many parameters of neural responses, is very has a capacity or conveys more information, but how to use it in practice? What are the parameters of the tuning curve that we need to keep track of in order to read out the neural responses? So in order to understand this, I would like to change the way we describe neural responses to another model. So usually when most studies, when they analyze decoding or how neural responses are read out, describe the tuning neural responses using the tuning curve. So we have preferred orientation of the neuron, which gives the maximum response, and then how the response probability goes down. An equivalent, completely equivalent way is to the so-called linear nonlinear model. So the model in the center is usually, one can find it in papers on decoding of how to read out neural responses. And the model on the left is usually used for encoding, describing how neural responses are structured and what is the probability of neural response given a stimulus. But actually, one can go their equivalent, mathematically equivalent, with some caveats. So what is plotted here is the stimulus component along the preferred stimulus for example, for this visual neuron, and the spike probability is a logistic function. It doesn't have to be exactly a logistic function, but we will discuss why logistic function is specifically useful. So now, in this common way of describing neural responses, we have two variables, threshold and the slope of this tuning curve. So let's see what happens when we change these parameters. So if we keep the threshold the same, but make the curve more shallow, then the width of the tuning curve in this representation broadens, and it also has now a smaller peak value and a broader baseline. If we change the threshold, then the peak also goes down, but the tuning width maybe changes less. It's also affected, but maybe less. But the bottom line is that if we change two parameters in the tuning curve, on the left in the linear nonlinear description of null responses, one can get a family of tuning curves, not the full family, not arbitrary shapes, but some variation, some subset of tuning curves. So why is this framework useful for understanding neural responses? Then it turns out that if this nonlinearity here is a logistic function, meaning it looks like this and is described by these two parameters, then mathematically, so I'm writing it out here as 1 plus exponential, and the argument of the exponential is the projection between the stimulus S and the preferred feature for the neuron W. So the W again is this picture here. And it has the coefficient beta, which describes how sharply this function is tuned. So when beta is large, this is a sharp function. When beta is small, it is a shallow function. And then there is a threshold. So if the nonlinearity of the neuron is structured in this way, then one can show that this model has an information-preserving population vector, meaning that and this vector is similar to the population vector that Georgopoulos proposed and is widely used, but it has one modification. In addition to weighing neural responses by the preferred stimulus pattern W and the responses R, we have an additional weighting factor, beta, which is the slope of this tuning curve. So that's now one can also work with the tuning curve representation on the right, but the relationship between parameters of the tuning curve and the width and the peak and beta, while it is 1-to-1, it's just a very complicated expression. So it's difficult to find it if one starts the theoretical analysis with the tuning curve description. But here, if you have a linear nonlinear model with a logistic function, then this parameter just appears, and you know, for example, that the threshold here does not contribute to the information preserving population vector. So one doesn't need to keep track of the neural thresholds when reading out the information. So this is kind of a take-home message, and now we will test it. And first, I will provide an intuition for why this works, and then we will test this equation in first in simulations and then in experimental data. So the claim is that if so it's possible to take a linear combinations of neural responses, because neural responses are a nonlinear function of the stimulus, but it is a linear combination of neural responses here. And this quantity is capturing all information there is in a given neural population. So how, yes?
Sorry, Tatiana,
Yes.
There is a question here from Toby Delbert. He's asking, but does the noise affect the information preservation for various beta? And that is, if there is noise, it disproportionately affects lower signal values if it's additive?
Yes, so we will go over, but this is a good time to address this question. So, exactly. So what does it mean, beta? Beta means kind of inverse noise. So when beta is large, the noise is small, and vice versa. So it says that it is kind of like a democracy, but weighted by reputation, if you will. So if a neuron is recently or on average has been more reliable and has less noise, meaning that its input-output function is sharper, for example, black or magenta curves compared to a blue line, then the responses of that neuron are taken with a higher weight. So another way of answering, another statement that I think is helpful here is that population vector is a random quantity. So neural responses are binary between 0 and 1, or 1 and -1, and they fluctuate. So even if we present the same stimulus S, the neural responses are stochastic, and so the value of the population vector will fluctuate. Nevertheless, when we monitor this variable captures what there is in neural responses. So it's not that information is infinite. So the neurons compress, for example, from stimulus to the neural responses. We have a compression and we lose information, but whatever is present in neural responses, you can read out using this random variable that is one-to-one related to neural responses, and this vector fluctuates. So when neural responses are noisy, then there will be a lot of fluctuations in this population vector. And so the overall information between stimulus and the neural responses and between stimulus and this population vector is small. Are there any follow-up comments in the chat?
No, I think you answered it well. Okay. So if there is any follow-up questions, please write on the chat. Okay.
Yes.
Thank you.
So I will try to provide a different intuition. So, it's often said that, neurons have, so each neuron has, for example, 2 binary responses, 0 and 1. Then we have 2 to the n values, and it's all very complicated. An astronomical number of patterns, and we cannot observe it or measure it well. So here is a simplification. So suppose our stimulus and the set of preferred orientations lives in the 2-dimensional plane. And we have 2 neurons, and this is their receptive fields or their preferred stimulus directions. So with 2 neurons, I can have 4 response patterns: 0, 0, 1, 0, 0, 1, and 1, 1. So what this picture shows is that I converted these patterns of responses, kind of a sequence of strings, to a position of 4 points, 4 values of a single, in this case, it's a population vector, and that takes 4 values. So it's a one-to-one transformation from neural responses to a values of this vector. Now, suppose we have more neurons. So here is a third neuron is coming into the picture. So initially, when this neuron is not responding, we get the same pattern. Now, if we take into account that there is a receptive field from or a third neuron that could spike, then when that neuron produces a spike, we get another set of 4 values. So overall, the population vector for 3 neurons can take 8 values, which is 2 to the 3. And now the population vector is a random quantity that jumps around among one of these blue dots as a function of the stimulus. And presumably it's not completely random. So some dots will be more visited by when the stimulus takes certain values. Now imagine that you have more neurons. So then we have 2 to the n values potential of this population vector. But if all of these preferred stimuli are in the plane, then the population vector is also in the plane. And so that's what we have. We have a value of a 2-dimensional vector that takes 2 to the n values. And what we will be showing is that one of the advantages of this approach that there is some continuity here. So you can actually coarse grain this. Suppose I don't want to monitor 2 to the n values, but the dots that are similar to each other, they if I merge them, then that's a good way of approximating information. So suppose instead of 2 to the n values, I only have say 100 values. So I will bin the values this plane into 10 by 10 bins and only monitor a reduced number, but it still turns out that it's still an efficient way of capturing information that is contained in neural responses. So maybe a comment about what's the difference between information preserving population vector and classic population vector. The difference comes in a case where you have neurons that have the same preferred stimulus, like this this neuron and that. Let's see, like that. So when their preferred stimuli are aligned. So in this case, whether neuron 3 produces a spike or neuron 2 produces a spike, you get 2 different patterns. Versus in the classic population vector, because we ignore the fact that neurons have different noise and therefore have different, so the length of this vector that represents the stimulus here represents the amount of reliability. So the bigger this vector, the more reliable is the neuron. So in the classic population vector, this is ignored. And instead of the 8 patterns, for example, for 3 neurons, we will have only maybe 6. So because these 2 patterns are merged together. So this is an intuition, my explanation for why this classic population vector is so popular, and it usually works very well, except when you look in detail in a focused neural population, then one would find information loss, like was found by the work by Bill Balick and Jonathan Victor. So now this is an intuitive explanation. Now I will show you simulations that test this readout, and then we will progress to experimental data. So there are 2 main conclusions of this approach. So we have this new readout, and for the readout purposes, all that it matters is that a scaling factor that represents the magnitude kind of receptive field or the stimulus but it's really the slope of the input-output function of the neurons. And the threshold, for example, doesn't matter. So now we can test these two assumptions, first in simulations. So the first set of simulations was designed to mimic the results from Steve Lisberg and Bill Bailey. So in this case, we have a model neural population that have the same preferred stimulus, so the same preferred orientation, and then the tuning curves have different widths, they have the same magnitude, and this is a reproduction of their results, where the classic population vector here, so we plot information versus the number of neurons in a population, and the classic population vector loses information compared to information preserving population vector, and the black line is the full information, and the dots is actually the coarse-grained version of the information preserving population vector to, for example, 15 bins. So up until 5 neurons, it's exact, and then there are small deviations. But it also shows you how, because the values of the information preserving population vector, they have some continuity into them. So if you bin them according to their values, even though we are now reducing the number of patterns, still the information loss is very small. Now here is another test. In this case, we have neurons with different preferred orientations, but for each orientation, there is a set of curves, a set of neurons with different reliability factors. And again, one sees the same effect, where information preserving population vector conveys more information than the classic population vector and matches the full information that one can exactly compute. So the next prediction is, suppose we have neurons, they have the same, again, preferred orientation, same preferred stimulus, but now we change this threshold, but we keep the reliability, this parameter in the input-output function, the same. In this case, the tuning curve changes shape, so they have now different peaks, and they have slightly different widths. Nevertheless, all the curves overlap. So classic population vector captures full information, which is the black line, and information preserving population vector is also equivalent. So this is an illustration or the claim that differences in threshold can be ignored, even though they lead to curves with different peaks. So there are papers that analyze how differences in the shape of the tuning curves matter for the readout, and that is true. But we also show here that not all variability in the shape of the tuning curve matters. And it's difficult to get the right parameter when you work in this description, but it's easier when you work in the linear nonlinear model. But they're equivalent. So another question sometimes comes up is people are concerned about the presence of correlated neural responses, in particular noise correlations. So now the answer is, how does this affect the readout? And the answer is sometimes it does and sometimes it does not. So with noise correlations, so we modeled the noise correlations that they were fixed. They differed between neural pairs, but they were fixed and depended and only depended on the preferred orientation of the two neurons. So with in the presence of noise correlations, the tuning curves now take very strange shapes. Nevertheless, you can use the same formula, and the information preserving population vector will capture full information, that there is in the classic population vector. The only constraint is that these noise correlations have to be independent of the stimulus. So mathematically, this is maybe a technical detail. It's not necessary. It's for people who want to implement this and specialize in particularly interested in noise correlations. So if we have neural responses as a function of stimulus, when this probability distribution can be described as a function of the stimulus times the function of responses times these noise correlations, but they do not depend on the stimulus, and all the stimulus dependence is in vector t that multiplies s. So that's a definition of the sufficient statistics and a derivation for why this vector captures whatever information there is in the neural population. So I will maybe show some application to neural data, and then also say the implication. We can now look at neural data, and then I will follow up with some predictions for how neural responses should be organized. So this is data that I collected when I was a postdoc in Michael Stryker laboratory, together with Ken Miller. And these are number of neurons and that were simultaneously recorded. And we can compute information directly, which is the black line, then as an information preserving population vector in red dots. And the spike count is in blue, and the classic population vector is in gray. So the reason this is more of a reproduction of results by Jonathan Victor, because here the neurons are recorded from a nearby region, so their preferred stimuli are not exactly identical, and therefore based on the differences in the preferred orientation, the classic population vector captures more information than there is in the spike count, but nevertheless it will lose information compared to the information preserving population vector. And there was a question in terms of noise and variability, so this is another way of addressing that question. So here is kind of an illustration of how the information preserving population vector or classical population vector, that these are random quantities. So what is shown here, each dot is the value of the vector. And the color means when they have the same color, it means the same stimulus. When they have different colors, means different stimuli. So you can see that qualitatively, if in the classic population vector, there is more spread in relative terms, and there was more mixing of different colors. And therefore, this classic population vector conveys less information. And there is less mixing in the information preserving population vector, and less scaled in relative coordinates. So now one of the predictions is that it might be good for neurons to structure their neural responses in this way, because if the nonlinearity is not a logistic function, then there is no information preserving population vector. So it will not be possible to transform neural responses. We imagine that there are multiple series of transformations, and you cannot, every time we transform, there will be information loss. So there might be advantageous to structural neural responses in this way. But because if we only are shifting the threshold and kind of the beta parameter, this does not lead to arbitrary tuning curves on the right. In particular, across, if we change these two of these parameters, either the threshold or the steepness, you get a dependence between the background spike rate, whether it is small or large, and the modulation in this curve. So the difference between large value, the maximum value, and the smallest value. So that's the, if we monitor this on this graph, so this is the lowest spike rate to kind of the stimulus that is 90 degrees from the preferred, and the modulation of the tuning curve on the x-axis. And so in general, so we see that either there will be a large background, or there will be large difference between the peak and the bottom of the tuning curve. And here is some supportive evidence. So this is in this recent neuron paper. So if you zoom into their highlights, we can see that neurons with strong multiplicative effects, the ones that modulate their tuning curves by a scaling factor, so that's between the maximum firing rate and the minimum firing rate, have weak additive floor in the tuning curve, and vice versa. So that's indirect evidence, I think, that supports this observation that what really neural tuning curves are trying to approximate is the logistic function. There are other predictions, and another prediction is that the decoder at the readout should connect more strongly to neurons that are more reliable. So now we have maybe 10 minutes, so maybe less. So I will talk.
Sorry, sorry, there was a technical problem here. Sorry, I wanted to unmute myself and I blocked the screen. We'll be back soon.
Okay, can you hear me?
Yes, sorry, I was going to unmute myself to tell you that we still have 10 minutes or a bit more if you want, but I ended up blocking you by mistake.
I see.
The
Okay.
icon, basically, it's a microphone and I pressed the wrong button. Sorry for that. If you could share your screen again, please. Yeah, sorry for that. That was me pressing the wrong button. But for sure, we have 10, 15 minutes still if you want to finish the second part.
Okay. Okay, sorry. Okay, so it is more technical, so I think it's, I will present a condensed version. So it's the point that we would like to discuss is how information is conveyed by large neural population. So we think we have a vector t, which is a random variable that actually has the same dimensionality as the stimulus dimensionality, or the set of neural preferred stimuli and preferred receptive fields. So the dimensionality of this vector does not increase with the number of neurons. The number of values that this vector takes increases. So you may have an extra resolution, but the dimensionality is the same. So now we have an equation. So I think it solves the so-called curse of dimensionality in terms of the number of neurons, because we can always coarse grain this value t, and as I have shown, it doesn't lose a lot of information. But we still have a difficulty when computing information between two vectors when they have large dimensionality. So that's the question that I will address in the second part, in the last part. So I will describe just numerical results on the three approximations that we came up with. Maybe there are other ways, but that's where we are right now. So, and these approximations are progressively less accurate and but more easier to implement. So if you start, what are these approximations? So if you start with the full information, it turns out, so this is information between stimulus components and population vector components. And they live in the same space. So they have the same coordinates. So for example, one can think of this S as having different frequencies in the stimulus, and then population vector T will also have the same frequencies. So just like when we load pictures over the internet, first you get a coarse-grained version, and then with time you get a more fine-scale information. So we can compute information in the same way. We say it's information between, for example, B is the frequency as the lowest frequency, and full vector T, and then information between the next frequency, again full vector T, conditional upon the previous component. So far it's an exact equality, but it's still difficult to compute. We made, based on the structure of this problem, you can simplify a little bit and actually observe that not all components of the population vector matter, but only some beyond the component of the stimulus. So for vector S0, initially you take all the T components. For the next frequency, you take one less of the components in the population vector, and so on. But it's still a difficult calculation, and it's difficult for two reasons. Because it's between one quantity, one-dimensional frequency, and still you have many components, at least initially. And then the conditional part is also very difficult. So for statistical reasons of sampling. So to approximate without without too much politeness, we eliminate all of these components and substitute them with the relevant component, which has the same matching component to the stimulus, plus the power in all other components of the population vector. And this approximation turns out to be exact if inputs are isotropic. So if we think about motion of a hand, then if you think that the hand is moving in a uniform way for all possible directions, then this will be an exact approximation. But if it is not, then there will be a loss. But that's one motivation for this approximation. Then the second approximation is to simplify and ignore this square root and this other power, and only consider matching frequencies in the stimulus and in the population vector. And we call it component conditional because information is computed between matching components in the population vector and the stimulus, conditional upon everything, all other components. And then third approximation is to ignore this all of these components, and it's easiest to implement, and it's exact if inputs are derived from the independent distribution. So it turns out this is most accurate. The green approximation, number 1, is more accurate, number 2 is less accurate, and number 3 is even less accurate, but they're easiest to implement. So here is the illustration of how this works. So the scale does not begin at 0, it begins at 4, but you can compute information for many neurons, up to 1,000 neurons. And black line is a direct full information by Monte Carlo simulation. And this green is isotropic approximation, so essentially the same value. And then the component conditional, and again component independent. But even component independent, instead of the value of, say, 7.5 nuts, or bits in this case, nuts, then you get 6. So it's within more than 80% of the information that is contained in the responses of this large neural population. So this is for 3-dimensional uncorrelated stimuli. Now, what is the difference? One can ask, in what order is it better to compute information? For example, one could think, first I'm going to provide, as in these examples of picture loading from the internet, first give a fine scale information and then modulation, or vice versa. And we know by experience that first it's more pleasant when they give you a low frequency information first. So here is the same phenomenon in information calculation. So the ground truth is in the black, and again we're looking at the information versus, in this case, 2-dimensional stimuli, and the ratio of where is the frequency, more power in what component. So up until the value of 1 here, and the first component has less power than the second component. So now we are looking at the ground truth is in black, the isotropic, this vector sufficient statistics full equation is, in this case, what we can compute because the stimulus is only two-dimensional, matches the ground truth. And here are the two approximations, component conditional and component independent. The component independent is, doesn't matter in what order you take these components, but there's an interesting crossover in this component conditional. So when there is more power in component number 2, because this ratio is less than 1, then the dashed line is more accurate, and the dashed line corresponds to computing information with respect to component number 2, followed by component number 1. And then they switch. So when component number 1 has more power, then you should take first evaluate information with respect to component number 1, followed by additional information from component number 2. So, and another analysis, so in this case, it is 100-dimensional stimuli. So we cannot compute any other approximation except for component conditional, component independent information. So this is full information by Monte Carlo simulation. And these are an approximation using independent components from natural scenes. And it's also very accurate, so between 8 and 6. So that's the magnitude of the effect that one loses by not taking full care of the information calculation. Kind of a cautionary subject here is that this dashed line is component independent approximation, but with PCA components. We know that natural scenes are not Gaussian, and so PCA components are actually not independent. And in this case, one can actually overestimate information. So in summary, what I have presented to you today is the formula for the information preserving population vector that adds weighting by neuronal reliability. And we think that it captures, it should work better than the classical population vector. It works with diversely tuned functions and also works with in the presence of certain types of noise correlations. And it has the same dimensionality as the stimulus, so does not increase with the number of neurons. And in the case, and as I mentioned, works in the presence of noise correlation, the same equation. So when noise correlations go up and down, then the overall amount of information that there is in the neural population goes up and down, but you can still read it out using the same formula. And there are 3 ways that one could approach. Maybe there are, hopefully there will be more work and more methods, but for now we have 3 ways to approximate exact expression to, in the case where the stimuli have high dimensionality. So I would like to say hello from my group. So this is before pandemic, we see. And John Berkowitz is the main person who carried out this work. Thank you for your attention.
Thank you very much, Tatiana, for this interesting talk. It was really nice to hear about this vector analysis. I have a question, and in the meantime that I ask the question, I would ask people to fill the questions in the box if there is any from the audience. So it's a bit of a question about how the neurons represent the stimulus, let's say preference. Like there is some work showing that the neurons actually change depending on context or other external factors, the receptive view, for example. It's not something that it's from learning, right? It can change it to responding more to a color than other, depending on the context. Would that be possible to incorporate? It's basically a different dimension in the stimulus. I don't know if it would make sense or.
Yes, I think one can incorporate this. The only limitation that I worry about is that it has to be a kind of a logistic function. So the moment and all of these dimensions has to combine linearly. W. So if one can write kind of a joint receptive field in terms of W times stimulus, and the stimulus can have color and sound information, but if it is with context dependence and something, I think, which is a limitation that we are trying to address, is that if you have nonlinear interaction between features, then no.
Okay. So there must be a linear component there too.
Yeah, so I think there might be. So what I'm trying to work now on is to generalize it to this case where you have different features that are interacting nonlinearly. But for now, that doesn't. The approach doesn't work for these neurons. So you can either one can either model modulation as a change in the threshold. So to the extent to which that works, then that's okay. But because if the threshold depend on another variable, then that will be difficult to capture information about both variables. Okay.
Okay, thank you. And one other thing. So from the plots, I see that it looks like the information content kind of starts to plateau at some point when you increase the number of neurons. Can you kind of draw some conclusions or predictions on what number, like what would be the optimal number of neurons that a given region would have based on that, and if it's comparable to data, for example, from sizes of regions?
Yes, I think it's a very interesting question. I haven't done in this version. I think it's difficult to compare, but I think once you take into account the modulation, if one can address that problem first, then you can have prediction for. So far, the argument would be towards lower dimensionality of the neurons, right? Because they saturate.
So would that mean that you don't need that many neurons or? Yes,
that's right. So I think it's a hint towards low dimensional neural computation.
I see. And so that would that hint on the fact that there is a lot of redundancy for large populations? Or?
Yes. So we have these receptive fields, and they are very similar, so they doesn't add information. And if the stimulus is high dimensional, then it's hard to compute the information. So.
Okay. Okay. So thank you again for your talk. I have the link here for the Zoom meeting that I'm going to paste again.
Okay, thank you so much. So I'm going to the Zoom now. Okay.
Yeah. So anyone who wants to join us, please enter the Zoom meeting. And thank you again for.
Thank you. Thank you.
Bye-bye.